we proposed an algorithm to classify textured images by using centroid computed with Kullback-Leibler divergence. The Kullback-Leibler divergence is a tool from information geometry. In the other hand, the Bayesian framework of classification is a collection of ways to classify data that is furnished in the literature. For instance, the Jeffrey-Prior distribution that is proportional to the square root of the determinant of the Fisher information matrix does not use the whole geometry of the Riemann manifolds. We introduce an framework from Bayesian classification and textured images and information geometry by proposing an intrinsic prior distribution. This intrinsic prior distribution allows us to make our decision on the data, on the hidden parameter space instead of the classical data space, reducing the computational complexity of the classification and leading us to the choice algorithm for classification for the textual images classification. We extend our intrinsic prior distribution to work with K-Centroids-Based classifier to reduce the impact of intra-class diversity. Intra-class diversity is due to various phenomena, such as differences in color repartition between the images, differences due to changes with elimination, or differences due to different scale and orientation of different perspectives. Textured images classification is a complex problem that and good performances could not be achieved without taking into account this intra-class diversity. In this talk, we will be separated in three main parts. First part, I will show links between Bayesian classification and information geometry. In the second part, I will introduce you to textured images modelization and classification. And in the third part, we propose our KCB classifier to reduce the impact of intra-class diversity. But first and foremost, we use an intrinsic prior distribution to define a monocentroid classifier. Let X be a random variable that follow a specific parametric model. The parameter space is a Riemann manifold thanks to the Fisher information matrix G. We assume also that parametric vectors follow a prior distribution, a parametric model. We have also large MC classes, and the fact that we belong to class A is coded by decision HA. The prerequisite to work with Bayesian decision will be the likelihood, the prior distribution, and the 0-1 loss function. In Bayesian estimation, however, we have a wider range of functions that works as a loss function. Our main goal in Bayesian decision is to write a decision rule on the data space. But here we use the likelihood. This means that in classification purpose, we would have several access to data by using several times the likelihood, and this increases the computational complexity of classification. And this is why we would prefer to make a decision on the parameter space instead. And this is why also we would use information geometry to understand the geometry inside this manifold. In textured images, a textured image is represented by a parametric vector that lies on parameter space. We suppose that all class of textured images are well separated in this parameter space. This means that a class of textures could be represented by a centroid and a variance around the centroid. Centroid would be is first order statistics, and the variance is a second order statistics. this parameter space that use both first order and second order statistics as a Gaussian distribution on Euclidean space could be done thanks to works of Xavier Pennec that defines that extend the Gaussian distribution to Riemannian manifolds. We here see the Rao distance, and the Jeffrey divergence we use here is equal to the square Rao distance locally around the centroid. Also, around the centroid, we will compute the normalization constant Zi, and we make appear the square root of the determinant of the Fisher information matrix, such as the Jeffrey-Prior distribution. But here we use all the geometry of the manifold by the use of the Jeffrey divergence. Our intrinsic Prior distribution is this concentrated Gaussian distribution with hyperparameters that are the centroid theta bar I and the variance sigma square I. Now, with a Prior distribution, we are able to define a decision rule on the data space. The decision rule consists by minimizing integrals that does not have a closed form. We will use a Laplace approximation of this integral that is optimal in terms of minimization. And with the use of a concentrated Gaussian distribution, the decision rule on the data space becomes a minimization of the normalization constant plus minimization of the ponderate Jeffrey divergence between the maximum likelihood estimators from data and the current centroid theta bar j. Our decision rule that we have done on the data space becomes in fact a decision rule on the parameter space by the use of the Jeffrey divergence. This defines a monocentroid classifier that we could use on high data case such as textured images. Recent works prefer to use wavelet decomposition to work with textured images. Textured images is decomposed in several scales of decomposition, and each scale is decomposed in several orientations of decomposition, leading us to several subbands. Coefficients from the subband are assumed to follow a specific parametric model that will be the likelihood used in Bayesian decision. In this work, we model the spatial dependencies by using the neighborhood of each pixel and storing this neighborhood inside the vector x. We model this vector x by a spherically invariant random vector. This means that the vector x could be shown as the product of the Gaussian, modified Gaussian distribution G and the square root of the invariant distribution to this invariant distribution, also called multiplier, are assumed to follow a variable distribution. Instead, in this condition, we do not have a closed form expression for the PDF. And we introduce joint distribution y that equals to G. And with the chain rule, we could explain the PDF of y. Now, the different divergences between two SIRV models is just a sum of the different divergence for the Gaussian part plus the Jeffrey divergence for the multiplier part. And computing the centroid would be just computing the centroid for the Gaussian part and the centroid for the multiplier part. For the Gaussian part, we will use works from Banerjee that defines, gives us a closed form expression for the left-sided centroid and the right-sided centroid for the Kullback-Leibler divergence. Nielsen and Nock produce algorithm to compute the centroid in sense of the Jeffrey divergence by using a dichotomy between the two, the left-sided and the right-sided centroid. We do not have closed form expression for the centroid for the multiplier part, and we also will use a steepest descent algorithm to compute it. We have now all tools to make our monocentroid classifier on textual images, and we introduce here a K-Centroids-Based classifier on textual images to reduce the impact of intra-class diversity. If we look closer to the shape of a class of textual images, Aurélien says that if we make some transform on the textual images, we could not stay with ellipsoid shape for the class and propose to use a multi-cluster to represent this class of textual images. But where Bombrun works with textual images, but without using a stochastic model on coefficient, we could use the same approach with a stochastic model on coefficient. This means that we just have to extend our intrinsic prior distribution by using a mixture of concentrated quotient distribution for each cluster of To compute all centroid for a class, we will use an unsupervised classification algorithm that, such as K-Centroids, repeats two steps until convergence. The first step here is assignment of each parametric vector to a cluster by minimizing the Jeffrey divergence to the centroid of the cluster. And the second step consists on updating the centroid. We are now able to make a KCB centroid classifier, and we compare the KCB classifier to a monocentroid classifier on classical textual images databases such as Vistec databases and Brodas databases. This figure shows draws evolution of the average kappa index as a function of the number of training samples. The red line corresponds to a nearest neighbor classifier. The blue line corresponds to a monocentroid classifier. The green line corresponds to who represents KCB classifier, where k equals 3. As observed, we have a significant gain of 5 volts by considering 3 centroids instead of 1. Moreover, we have KCB classifier performances that is close to nearest neighbor performances, but with reduced computational complexity. In this table, show the kappa accuracy for both Vistec and Brodas databases. The first line corresponds to classifiers that use a SIRV model to model spatial dependencies, and the last lines correspond to an univariate model, and this more precisely it's a generalized quotient distribution. As expected, classifier based on the multivariate model outperforms classifier based on an univariate model. Not so the good performances of the KCB classifier noted in bold. In this work, I have introduced links between Bayesian classification and information geometry that apply to textual images classification. We propose a concentrated quotient distribution that allows us to make good decision rule on the data space instead on the parameter space instead of the data space, and also reducing the computational complexity of the classification. We also propose a K-Centroids-Based classification that allow us to reduce the impact of the intra-class diversity on performances of classification. We have KCD performances that is close to nearest neighbor classifier, and with a reduced set